Hello physics students. In this video we're going to look at a new kind of motion. Most of our time so far has been spent talking about objects moving at a consistent velocity or speed. So for long stretches, for periods of time, objects have been moving at the same speed or same velocity. Now we did have some problems where that velocity suddenly changed to a different one. But then over a stretch of time, either like 10 seconds or 10 minutes or longer, that velocity or speed continued. Whenever you have stretches of time in which the speed or velocity has remained consistent, we tend to call that constant velocity. What I have here is an animation called the moving man, whose only job in life is to essentially show different kinds of motion, exhibit different sorts of motions. So if you look at the top frame here, you'll see the moving man is in a suit on the left-hand side. He's to the left of the tree. And if I hit play on this animation, he's going to move with a consistent velocity, a constant velocity. You'll see there's a red arrow at his feet. That red arrow is a representation of the velocity. The size of the arrow indicates how fast he is going, and the direction of the arrow obviously indicates which way he is going. So if we had a different velocity, say I made it a faster velocity, that arrow would actually be a longer arrow. But I want to show you a consistent velocity here, so the arrow will stay the same size. So if I hit play, you'll see that he moves across the screen at a consistent velocity. And in fact, he moves across at a velocity of positive 3 meters per second. So that means that he's changing his displacement by 3 meters for every second he is traveling. So if I rewind, notice how if I were to advance the frames manually by moving the slider, advance it by 1 second, he started in this negative 10 meter location. He ended up over here, which is probably around negative 7 meters. And notice how he covered 3 meters worth of displacement in 1 second. So if I were to advance to the next second, ooh, that's exciting. Advance to the next second. Notice how he is now located here at negative 4 meters. And he's a total of 6 meters away from where he started, right? So 6 meters of displacement. And that makes sense if he's moving at a velocity of 3 meters per second, because his displacement changes by 3 meters for every second of travel. Since he's traveled for 2 seconds, his displacement has changed by a total of, that's right, 6 meters, because again, it's 3 meters for every second. Anyway, so this video is showing a nice constant velocity, a consistent pace all the way across. But that's not the only kind of motion that one can see. Another kind of motion that we'll experience this year is something called an acceleration. Now, the good news is most of us have a gut feeling for what acceleration actually entails because we use that word in everyday language. However, there are going to be some slight differences between how we use the word acceleration in everyday language and how physicists use the word acceleration. We're not going to spend a whole lot of time with that nuance in this video, but we'll talk about it later on. If you take a look at the animation down here on the bottom, this is going to show an acceleration. And in fact, it's going to show a consistent acceleration. And acceleration in physics just basically means that your velocity is changing. So as time goes on, we should see that his velocity is going to vary. Remember, we're using a red arrow here to show the velocity of the moving man. So if he's experiencing an acceleration, which means a change in velocity, we should see the size of that velocity arrow change. Well, let's go ahead and watch him accelerate across the screen. Notice how the velocity arrow got bigger as he moved across, because he was getting faster and faster. This is what we call acceleration. And more specifically, this is what we call a consistent acceleration, because it turns out he gets faster and faster by the same amount in each second. A consistent acceleration in physics is sometimes called a constant acceleration. And that can get a little confusing because clearly acceleration means something is changing here. And you have the word constant in front. That makes it sound confusing. But constant acceleration just means, hey, his velocity is changing by a consistent amount as time goes on. So these two different motions we're going to look at a lot this year. And I thought it might be worthwhile to watch both motions happening at the same time so they can kind of compare them. So I'm going to start the constant velocity, and then I'll quickly start the acceleration and go ahead and watch what they look like when compared. You'll notice that in the accelerating case, the moving man actually passed the other one that was moving at a constant velocity. And that kind of makes some sense because remember, in the accelerating case, he's getting faster and faster. So at some point, he's going to have a velocity that's greater than the man that was moving at a consistent velocity or a constant velocity. So you just saw, again, an acceleration. In physics, we define acceleration as the rate at which velocity changes. Now keep in mind, there are two aspects to velocity because velocity is a vector. It has both a magnitude and a direction. So if the magnitude changes or the direction changes, we consider that an acceleration. Or, in exciting cases, you could have both changing and it's still considered an acceleration. So the key thing is, acceleration is measuring the rate at which velocity is changing. Now we want to be able to calculate that rate, and so we have a formula. The formula says that the acceleration A is equal to triangle V over T. What do you think the triangle stands for? That's right, it's actually the Greek letter delta, and it stands for a change. And then the V stands for velocity, so it's a change in velocity divided by the amount of time it takes for that change in velocity to happen. We can expand the delta V. Sometimes this is useful, and so we could write the delta V as the following. We could write, well, hey, delta V is really a change in velocity. And so you're going to have a velocity at the end, which we call the final velocity. You're going to have a velocity at the beginning, what we call the initial velocity. And if we subtract those, that should be the change in velocity. And then we can divide that by time, and that will give us the acceleration. So that's sometimes a useful formula to write out, Vf minus Vi over T. You could even write that in your reference tables if you like, next to the delta V over T that you find in the mechanics list. So here's where the acceleration formula is located in your reference tables. I'm going to take a look at the mechanics section, which is the last page on the back. Here it is. And then the second equation down is acceleration equals delta V over T. And again, you could also write next to that, that's equal to Vf minus Vi divided by T. Now, acceleration happens to be a vector, which means acceleration itself is going to have not only a number and a unit, but also a directional aspect to it. And then the units for acceleration are meters per second squared. Now that's pretty strange, right? We'll talk about why those units come about in an example problem. Let's take a look. So Mr. Nadeau's vehicle, which happens to be a Scion XA, is moving at a velocity of 20 meters per second west. Suddenly, Mr. Nadeau puts the pedal to the metal and accelerates to a velocity of 30 meters per second west, all in a time span of 2 seconds. What is the acceleration of my vehicle? So to figure this out, we're going to go through the steps of solving a physics problem. The first thing we have to do is draw a picture, of course. And so I'm going to go ahead and do that real quick right now. So I've got my car, and I have it set up so it's moving to the west, right? Compass direction wise, west would have to be to the left on the page. And notice how I have these green arrows up here. These green arrows represent velocity. Notice how I have a green arrow here that is smaller than green arrow here. That represents the fact that I got faster, right? So I started at 20 meters per second, end up at 30 meters per second. This blue arrow just represents essentially my displacement during that time, so how far I traveled and in which direction over the course of that. Not terribly important right now because the displacement is not going to play a role in my calculation, but I just thought I would write it out. So now we're going to go ahead and write our list of givens, the things that are given to us in the problem. We're clearly given the time in which this happens, so I'll write t equals 2 seconds. We're also given some velocities. Now, these velocities we're going to write with the VF and the VI that I showed you in the previous part of the video. Remember, VI stands for the velocity in the beginning. That's the initial velocity. VF stands for the velocity at the end, the final velocity. So I'm going to identify which of these is the starting velocity, which of them is the final velocity. And by the way, before I identify that, what kind of velocity is this? When I talk about instantaneous velocity or average velocity, right, as the two kinds, is the initial velocity and final velocity, are they average or instantaneous? That's right. They're an example of instantaneous velocity because both of these are velocities at a moment, at an instant in time. So now let's identify. So I start at 20 meters per second, right? So that's my initial velocity. But notice how I have a direction, west. I can't plug west into my equation. So what should I do with that? Good, I should put a negative in front of my 20 meters per second, indicating that is to the west. And then my final velocity is 30 meters per second. And again, it's west. So I will put a negative in front, indicating that you're traveling to the west. Now, what are we trying to find here? We're trying to find the acceleration. So I'll use the variable symbol for acceleration and write a question mark. Okay, now we need an equation that allows us to plug in time, initial velocity, final velocity, and get acceleration. Well, you just learned the equation, so it's easy to identify. The equation looks like this. And why don't we expand out that delta V, that change in V? Okay, now we're ready to plug in our information. And remember, when we plug in our information, the Regents requires us to substitute our numbers in with units to get full credit on the constructed response of the Regents exam. Now let's do some math. We have negative 30 minus a negative 20. Now, whenever you have these two negatives next to each other, what happens? That's right, it becomes a plus. So we're going to have negative 30 plus 20. And that comes out to negative 10. And I'm running a unit here, meters per second. You technically don't have to do that, by the way, according to the Regents rules, but it's going to be useful when we figure out the units later on. All right, so negative 10 divided by 2 is negative 5. And again, we said the units for acceleration are meters per second squared. So here's our answer. Now, I want to tease out what this means. So we have negative 5 meters per second squared. Well, first of all, let's figure out where I got the meters per second squared from. Let's think about the units for a second. So I'm going to come over here and think about the units in my equation. So I'm going to circle these. So I'm going to think about the units in the equation. We're going to kind of ignore the numbers for a second here. If I think about the units in my equation, I'm taking meters per second and dividing it by seconds. Now, technically, this is one way you could write the unit for acceleration. So I could technically write negative 5 meters per second squared as negative 5 meters per second. And that's technically acceptable. I could do that. And sometimes that's useful because this really gets at the heart of what acceleration means. This means that for every second of travel, my velocity changes by negative 5 meters per second. So for every second of travel, my velocity changes by negative 5 meters per second. So that's what that unit really means. And again, sometimes this way of writing it, this format, gets across the conceptual idea really well. And so sometimes I'll have it written that way, just so we can think about what the acceleration means. But if you know anything about mathematicians, they kind of freak out about complex fractions. Fractions within fractions are usually not okay with them. They usually get pretty upset about that. So this is where the meters per second squared comes from, because we have meters per second divided by seconds. And we do keep, change, flip. You may remember that from prior math courses. You keep the top, so meters per second. Then you multiply by the bottom. However, we flip the bottom, because really seconds is the same thing as seconds over 1. Because remember, anything by itself can be given a denominator of 1. And so if I were to flip that, I have 1 over seconds. And now if I use dimensional analysis, treat units like algebraic variables, I'm going to have meters times 1 on the top, seconds times seconds on the bottom, and that's how we get meters per second squared. That's how we get that acceleration unit, which looks so strange. But again, it's worth reminding yourself that really that represents meters per second, and that tells you how much the velocity is increasing or decreasing every second. So in this case, the velocity was increasing by 5 meters per second for every second I was traveling to the left. All right, well, that's all I want to talk about today. We're going to take a look at some examples of using this in class and give you a better idea for what it means to talk about these numbers associated with acceleration.